Hi everyone, we are back and let's go through our Pset solutions. I know this is a little bit longer one, but we'll go ahead and get through it or just show you some examples and then move past. Alright, so let's go ahead and look at what we've got here. So first off, let's write the dimensionalities. This is 0D, 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 1D, 1D. What else? Grain boundary 2D, Frankel 0D, 0D, stacking fault inner 2D. Twins 2D, voids 3D. So what do we have? So I could see a vacancy here. This is a impurity interstitial. This is a substitutional impurity. This is another impurity interstitial. This is a substitutional impurity. This right here is a self-interstitial. I see a little bit of a grain boundary, or not a grain boundary, excuse me, an edge dislocation right here. And I've got grain boundaries right here and here and here. So you could see oriented this way, now oriented this way, all those good values. So that's number one, not too bad. When we're looking at these defects, you can kind of see here that when I have this self-interstitial, it is going to push away the atoms from their equilibrium positions here. So that region is going to be very, very compressed, as opposed to here where we have kind of a region in tension where all these atoms are going to be pulled back in, relaxing back to other positions. So whenever we have that interstitial, high region of compression, same thing with edge dislocation, compression here, there's a little bit of space here, tension as well, but we're going to be getting into the stress fields associated with lattices when we get into lecture 9. So let's zoom in a little bit. Let's see if I have that power. Excellent. So I am going to choose my vector coming out of the board. So I need to do my right-hand rule circuit. So I'm going to go start right here. Actually, I'm going to start like right here because I'm going to be lazy today. Oops. Let's zoom in a little bit more. Let's see how far can we go. All right. Oops. So I've got my tangent vector. I've got my starting point right here. So, oops, I'm going to actually undo that. Oops, so I'm going to pick my start just right. Oops. Uh-oh, not responding. Hopefully, okay, let's see. All right, so I'm going to pick my start right here, and I'm going to start to go across. So I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So I went 4, 1, 2. That's my end. What is my rule? I am right hand start to finish. So my start to finish vector is pointing where? Out of the board, parallel. So that is a what type of screw? Right hand screw. I'm going to go again, coming out of the board like this. Pick my starting point. I'm going to just do it right here. I'm going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So my not complete. So what is my Burgers vector? Make it black. So I'm doing my start to finish. What's the relationship? Perpendicular, edge. And finally, let's go over here. I'm going to draw my line vector, my tangent vector, coming out of the board like this. So I need to curl around. So I'm going to go, again, place my start right here. I'm going to go 1, 2, scroll up just a tiny bit. Oops, very difficult. I'm at high magnification. There we go. So I'm going to go 1, 2, 3. Then I'm going to go, let's go here. Oops. Oh, it's very difficult. Actually, let's go 1, 2, 3, 1, 2, 3, 1, 2, 3. Ooh, let's go. Actually, yeah, let's do 1, 2, 3. 1, 2, 3. So we'll close that up right here. So that's my start. This is my finish. So when we go across, where's my vector? Start to finish. And another right hand screw. There we go. Now let's zoom out. hopefully we all enjoy that view. So let's just go to 100%. Let's go over here. Fantastic. All right. Now I've given you actual vectors and lattice, or actually vectors, tangent vectors and various vectors. So I'm going to do this a little bit systematically. So I want to solve 1, 1, 1, 0 dot 0, 0 minus 2 set equal to norm of, actually, let's just leave it. Actually, let's do a equals 1, 1, 0. Let's say b equals this. So let's do a dot b. A dot b. Norm is just going to be my norm of a, norm of b, times cosine theta. Oops, I'm going to do that. Thinking. I just quit my kernel. Always good before you start to get those values. So let's just look at this numerically solve. Basically, so this is my value. Actually, let's not do numerically solve. So my values is pi over 2. What is cosine of pi divided by 2? 0. So what is that dot product 90 degrees? It is what type of defect? It is going to be perpendicular. So that's my 90 degree angle. So I could just do, if I want to convert pi divided by 2 times my 180 degrees divided by pi, 90 degrees. So there we go. So that is an edge dislocation. So let's go ahead and look at 1, 0, 1, 2, 0, 2. Let's solve this one. 2 pi, 180 degrees. So this is what? Parallel? Right. Right edge dislocation. Right screw dislocation, excuse me. So what about number 3? 0, 1, 1. And then 0, minus 1, minus 1. Minus pi. So these are anti-parallel. So what are we going to get? You guessed it. Minus pi. Minus 180. So those are left screw. So number 4, 1, minus 2, 0. And then here we go. 1, 1, 2. Solve for this. And I'm getting something again that's going to be a mixed. What about this one? 0, 2, minus 1. And then 1, 1, 1. Solve this again. Another non-zero answer. So those are going to be, again, a mix of screw and edge dislocation. Mixed defects are much more commonly observed. So again, we'll see that when we get to closer. Material X has a stacking of ABC. So I know that is what type of material? You guessed it, FCC. What about ABA? That is going to be HCP. So we've got the crystal structures. So ABC, I process it, ABC, and then AB. So there's one that's missing. So that is an intrinsic stacking fault defect. Why? Perfectly fine. Nothing to worry about. Now, let's get into number 6. So we're going to do it as kind of systematically as possible, but let's go ahead and take a peek at what we're working with here. So let's go ahead and pull out some data files. So let's take a peek here. Let's look at my downloads. Where are we at? Here we go. So these are my raw data files. So dat equals this. I'm going to do, always a little bit frustrating to work with this. 1, 2, and finally look at 3. So I need to import dat 1 data. I want to flatten as 1. So first, I'm just going to import this data and convert it to files, basically, that I can work with. So I want to look at 3, let's look at 1 to 10. So let me do full screen here. All right, so I've got time and I've got force. So I want to make a stress strain plot. So I was pulled, basically the strain rate was 0.003 meters per meter second. So I could take that time value and I could, actually let me just double check, because there were some on Canvas, some updates, and I want to just make sure that we are reading the most up-to-date version of your problem set. Let's go to our values here. As you see, I need to grade your problem sets, but that is got one down. So let's look at here. Now, let's take a peek, just so that we're aware of what's happening here. So let's get to number 6. Yep, and we have a cross-sectional area of this, 4.27 times 10 to the minus 5. So I'm going to go ahead and write that down now. So A1 equals 4.27 times 10 to the minus 5. All right, got area 1, and then I know that my strain rate, so E dot equals 0.003. So what I'm going to do in order to get to stress and strain, so first off, I'm going to take 1, 2, 3. I'm going to start with the third value. So again, I'm going to say that my strain 1 is going to be equal to all of this good stuff. So I need this 3 to minus 1. And I want all the columns, or all the rows, excuse me, and I want the first column. Let's see. So that's not strain, that's actually time, but I'm going to multiply that by my E dot. And that's going to give me my strain. So I've got my strain. My stress one is going to be equal to the same thing, except, so this is force. What was that force in? Let's take a peek back at this. So what was that force in? Force is in newtons. Okay, very, very nice and clean there. So my force is in newtons, so I am going to do, I want the second column, and then I want to do divided by A1. So that's going to be my stress. So now I can visualize that, so I could transpose, actually plot, transpose, strain 1, because that's going to go my x-axis, stress 1, and then voila! I've got my material. So let's do a very similar procedure, and let's get the second data set. So that 2. So now I have displacement. So it is telling me that my original length is 4 inches. So my L naught for data 2, so L naught 2 is equal to 4 inches. So 4 times 0.0254 to convert it to meters. Let me double check that, but I'm pretty certain of that conversion factor. Inch to meters, 0.0254. Yep. So that's my L naught. My cross-sectional area, let's take a peek at that. So let's look. It is a thickness of 1/8 of an inch and a width of 1/2 an inch. So my A2 is equal to a width of 1/8, so 1/8 times 0.1. 1 divided by 8 times 0.0254 times, it's 1/2 an inch. Width of 1/2 an inch. Yeah, 1/2 an inch. So 1/2 times 0.0254. And what do you know? It's very similar to our other values. Anyways, so that's my A naught, my L naught 2, and I see that I have displacement. So this is my delta L, and this is in millimeters. So I really should have stuck with that in meters, but again, so what we're going to do for strain 2, I'm going to do the same procedure here. I'm just going to change it. Strain 2, stress 2, 2, 2, and then let's do, I think that's pretty well done. So this is my displacement, so I need to multiply this times 10 to the minus 3, because that is in millimeters, and I need to divide that by my L naught 2. So that should give me my strain. My stress is already in newtons, thankfully. Divide by A2. And let's go ahead and do that. It's thinking, strain 2 stress 2. Oops, let's do plot range all. Ooh, that's a big boy. So that should that's a lot of strain. All right, again, let's do number 3. And this is how you should really always approach, grabbing data. All right, so this looks like a short data set. What about 3? What about 4? Oops, so there's only 2 points in this data set, so don't ever say I don't give you an easier problem. So I already have stress and MPa. So again, I'm going to take this. I have my strain already there for me. So actually, I don't have to work with that too much at all. Strain 3. Then so again, already strain is calculated, so I don't need to do anything to this material. So strain 3 done. And then in terms of stress, I just have it in megapascals, so I don't want to do that times 10 to the 6th. So I want everything in pascals. And then I could just do the same thing here. So Mathematica doesn't have to be too, as you see, this isn't too arduous. This line plot. All right. Oh, I don't want 3, excuse me. I want, see, this is where you could get in trouble. So I want 2 to the end. So now I could, and that's a very, very straight line, but I wonder what material that might be. Ceramic. It's a ceramic. Anyways. So again, very, very similar data set here. Strain, stress, I've got it. I can plot it. And strain 4, dat 4. I want to get rid of just the first, so I wanted to go to 2 to -1, so fantastic, everything else is fine. And I could do my list line plot here, and then get those values. Strain 4, stress 4. Voila. All right, so I'm going to do most of these calculations. So plot the stress strain curve. So let's calculate some of these values. So I'm going to do it for the first one, and then I'm going to assume you'll do the rest for the rest of yours. So I could look at this plot, and I can do a couple of things. So I can go ahead, and I could just, if I want to calculate my Young's modulus, I'm just going to grab these points. I'm going to do fit. So I'm going to do fit 1, x to my data for x. And I get about 60, oops, let's see here. So as you can see here on this curve, I get about 60, it's actually a little bit less. So let's actually do that one more time. You could do this a little bit better, but I'm going to just do an approximation. So yeah, about basically 0.7 gigapascals. So this may be a very, very, very basically small polymer, or weaker polymeric material. Let's do the same thing for here. So you could do the same thing. But again, I already know what this material is. So again, I could calculate my Young's modulus like this. I could pull out some values. So I know basically once I start to lose linearity here, I'm going to grab that. That's kind of my yield stress, my ultimate. So, oops, should have copied that. Grab it, copy, Control C. So this would be my yield strain. This would be my yield stress. What is my, I could look at stress 1. Stress 1, actually do max stress 1. So that would be my ultimate tensile stress. My failure stress would be right over here, as you can see on my cursor. And yeah, so those are essentially some of the values that you're looking at here. So you can kind of see this is a little bit of a funky stress strain curve, but anyways, that's the data that we have that we're working with. So let's see, did we answer most of those problems? All right, yield stress, yield strain, failure, ultimate tensile strength, failure stress, failure strain. So again, you see it fails around close to 0.8. Again, that's kind of indicative of more of a polymeric material. So again, it could be a polymer, probably is polystyrene. Actually is. This is also polymer too. Why? Such a large stress strain here. Here, ceramic. This guy, metal. And you could confirm that. And I'm not going to go through all the calculations, but you kind of get the picture of what we're trying to do here. So I have this value. So this is MECH1. I need to calculate what is my, because we've already done this first part. I need to do elastic strain energy and toughness. So I am going to need to figure out, all right, what material, actually, let's go ahead and find that out. I'm going to need to figure out how do I calculate that. So I'm going to do that one. So I'm going to do interpolation. That one. So here's my interpolation function. So this is my fun1. So I need to do integrate fun1. Actually, let's do and integrate function 1 from, let's look at the interpolation. Then we can look at some integration. Always useful to kind of look back through. So we have our function, our interpolation function. We could plot it. And we could do some integration as well. Interpolate. There's some integration values. But anyways, we could start to let's integrate function x numerically integrate. So let's numerically integrate this function of x, and we'll go from x goes from, oops, let's numerically integrate this from x goes from, let's say 0, let's see what it will last it is, 0 to 0.78 seems to be the last point. Let's see if we get this. All right, so that would be our toughness. But if I was to look for the elastic strain energy, again, I'm going to only look in the elastic regime, and unfortunately, it seems like nope, here it is the value here. So, oops, so I could use this point here from 0 to here. Let's see if it gives me a value. So you can see the values are less. So that would be my elastic strain energy per meter squared. So let's go ahead and now you could do that for now the rest of the materials. So you can figure out which is strongest, most ductile, brittle. But we could see from the plots here, actually let's go ahead, let's see what is most stiff. So again, you could do that. This material is going to be a little bit less stiff. Let's do a fit here. So fit, oops, I just want to do fit. And I want to do this from 1 to x, x. So you can see that this is a little bit less stiff here, or less stiff than this, so it's more compliant. I could definitely do the fit. Let's look at here. 2 points, fit. What material is this? Ceramic. So you see it's a little bit still not super stiff. Oh, why is that? Because why is it the exact same value? Because I forgot to copy. Hopefully that didn't do the same thing over there. I think I got that value much, much more stiff. So we're looking at 281 gigapascals. So quite different there. And then finally, we can look at this metal. Oops, I gave it away. It's metal. But we said it here 1x x. So again, that's actually quite a stiff metal. But anyways, yeah. So so this is a metal. This is the most stiff. This is the most compliant. This is the most ductile. This is the most brittle, etc., 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 etc. So you know how to kind of complete the rest of this here. What type of material could each stress strain curve represent? Again, we talked about that already. Now this problem. I really, really, really like this one because you can kind of see what's happening with these stress strain curves. So let's go ahead and let's do it for, so I know that we have an expression that we actually talked about in class that we could relate my true stress. So my true stress equals my engineering stress, so I could do my stress 4, for example, 1 plus strain 4, my engineering strain. So that's my true stress, my true strain, true strain, true strain equals, and we saw that that was simply going to be, my true strain was going to be in the natural log of 1 plus my strain, engineering strain 4. So true stress, true strain, I could transpose this, and I could also transpose this guy as well. We'll plot these together. True strain, true stress, true stress. Voila. So you see the value is always higher than your engineering stress, which makes sense. So you can do that for all the other values. There's a cool one for the polymers, actually. It looks really, really, really cool. And you'll see that in a little bit. Actually, let's do that just very, very quickly. I'm just going to so our polymer, so strain 2, actually stress 2. Stress 2, strain 2, 2, boom, boom. I'm going to take this, keep that, but I'm going to do 2, 2. Let's see what we got here. Wow, look at that polymer. Unbelievable, right? Oh, it's so cool to look at that. So you see the huge extension that kind of goes along with that. But anyways, really, really, really fun stuff. All right, so that pretty much takes care of the problem, except I'm going to do the 0.02% yield strength calculation. So again, what does that involve? So I'm going to take this value. So let's see, where was my slope that we found for the first problem? So I'm going to take this value of my slope. So that's my Young's modulus. So I'm going to have this function, except I'm going to offset it. So this is my 0.02. So 0.02%. So it's going to be, my function is going to be this plus 0.02. Let's just make sure. 0.02%. So 1, 2. Yep. So I am going to plot along here. I'm going to do show the same one. Plot of, what do I call this function? 0.02. 2, or x goes from basically 0 to 0.8, and 0 to 0 to point. Actually, I'm going to switch this order. And I could see where it crosses, and again, you see, well, actually, we're kind of a little bit cheating, so we should do it 0.02. So plus 0.0255. That's 0.0255. Where is it? Sorry. Let me start off here. Actually, we have stress 1. Stress 1 does indeed start at 0. Actually, strain 1, excuse me. Yeah, we do start at 0. It's weird how it doesn't show. It's not looking like that. But anyways, that's our 0.002 offset. So again, I don't like that definition. So that's my whole point for that exercise. So fantastic. So let's get to the other problems. Draw the following stress states. So let's draw our RVE. Here. So this is my 1, 2, 3. So I'm going to be compression here. I am going to do a minus. So again, sigma 1, 2 corresponds to what? Is equal also to sigma 2, 1. So if my normal's in the 2 direction, I need to point in the 1 direction. So actually it's going to point over here. And then here is going to point over here. And if I also look at sigma 1, so the normal in the 1 direction going in the 2, it will point over here, over here. So that would be my sigma 1, 2s. My sigma 2, 2 is going out of the board here. And my sigma 1, 3 would be what? So again, sigma 3 going in the 1 direction Be positive here, negative here, and then my sigma 1, 3, so the normal in the one direction but pointing in the 3 would be like this. So we can look at that one. Let's go ahead and write this. Let's do the next one as well. So I could go ahead and draw my coordinate system, my cube here. So for my normal stresses, I see that I have 2, 2 in compression. And then, again, I still have my sigma 1, 2, which we drew previously. And then now I have here, and then we've drawn previously. And then here, let's draw this one. So negative 2, basically, so 2 and then the 3 direction. So on this positive face, it'd be down. This one would be up. If we do sigma 3 and then 2, it would be this way. There we go. And we've already drawn these. And you can look at those. We've already drawn all these. Again, you can kind of get the picture from here on out. Your graduate classes. So, what's my stress tensor here? Well, I've got this negative stress, so minus 55 here. I've got, what is this? So the normal is 2 in the one direction, 3. So that's my positive face, so 78. 78, although it's missing, I should have, what else? To be technically correct, what should complete this? So that's 2, 3. What about 3, 2? Normal here, so 3 and the 2, so it'll be like this. To maintain my equilibrium conditions. So 78, 78 minus 55, and then positive 2, 2. All of this in MBA. Fantastic. All right. This is not correct. We need to be symmetric. This one looks all good to me. I like it. I don't like this one because it's the same values. This one here, not symmetric. What about here? I'm all good. There we go. All right, now to everyone's favorite problem. So if I look at my potentials, so I have potential 1. So I have U1, that equals minus sine of 0.96 plus R, and then close it, plus 0.64 times R to the cubed. And then my U2, not the band, although I like the band as well. Very nice. I hope they're doing okay. I mean, I haven't listened to U2 in a long time. Maybe they're passe, but anyways, I'm old. That's the point. All right, so I've got U1 and U2. So I need to figure out which material has the larger Young's modulus. They're both FCC. So I could use my energy calculation, but I want to be a little bit lazy, so I'm just going to do my typical Young's modulus, which is just going to be 1 over my R naught value, and then the second derivative. So I need to find what is my R naught U1. So how do I do that? Take the derivative, U1 with respect to R, set it equal to 0, solve. And then I'm going to just actually evaluate this on another line because I don't want to get that value. So, oops, what's happening here? Well, I want to solve for R, and then I want the reals. So here's my value in nanometers. So keep that in mind. So that's my value in nanometers. R naught U2. So I can do that times 10 to the minus 5, but again, it doesn't really matter. Times 10 to the minus 9. I just like to have everything in meters. I can do the same thing for U2. And then it's 0.43. So minus 9. Oops. Let's get this value. Actually, I'm going to keep it in nanometers because I need to plug back into my expression. So this is all in nanometers. So my E U1 is going to be equal to 1 divided by R naught U1. And then I'm going to do the second derivative of U1, second derivative, and then I'm going to plug in slash dot R goes to R naught U1. So that's my Young's modulus. This is my, for U2. U2. So my second material has a larger Young's modulus. How will the Young's modulus change with temperature? Again, it generally decreases because, again, my potential curve will also change as a function of temperature. And also, you should expect that your R naught value will change as well. It'll expand. So that value should decrease as well. Excellent. So I'm all experts. So let's look at the following cool expression. So I've got my U3, I'm going to call it U11, equals A times 1 minus exponential minus alpha times R minus B. And then close that. I'm going to actually close it like this. Close it, close this, square it, and then minus 1, and then that. So now it looks pretty correct. All right, so what is the equilibrium distance? Again, I can find that. So my derivative u11 with respect to r, set that equal to 0, solve this for my r reals. So r equals b, so my r naught u11 equals b. So I've got that. What about the Young's modulus? I could do that as well. I mean, or I could also look at the energy binding paradigm. So my cohesion energy is the same as my energy binding. So my energy equals Z divided by 2 times my, basically, what is the value of my potential? So U11, and I'm going to evaluate that slash dot R goes to R naught U11. So when I do that, and then what is my Z, number of nearest neighbors for BCC? 8. Get that value in here. All right. Now, what is the Young's modulus? So my E11 is just going to be, I'm going to take this equation here. I'm just going to switch it for R naught U11, D11, R naught 1, and there we go. So my energy, so my EC, energy of cohesion, is 8.7, and then I'm going to change that times 0.602 times 10 to the minus 19th. I want to change that to joules. I need my values in joules. So that's my energy of cohesion. My lattice parameter, what is A already defined here? What is A? Let's see. Yes, let's clear A. So my lattice parameter A, which is equal to 3.615 times 10 to the minus 10 angstroms. I have a relationship there as well. We'll get to that in a second. And my Young's modulus, so my E for material 11 equals 300 times 10 to the 9. So if these are the case, what is alpha, A, and beta? Well, I have 3 unknowns, but I have 3 equations. So my EM11, set that equal to E11. My A for BCC I know is equal to 4 times R, which is my, R is my what? So my equilibrium distance, that R naught, is always 2R. So, for example, I know that my lattice parameter A is equal to 4R over square root of 3. My equilibrium distance, my R naught, is going to always be equal to 2R. So this is equal to R naught. So I could plug in and write A equals what? 2 times R naught over square root 3. So plug that in. So 2 times what? My R naught is just my R naught U11B. U11 divided by square root 3. And then I also want to solve what? I also want to solve that my EC is equal to my energy. So let's plug in the value energy. And what are we going to solve for? We're going to solve for A, alpha, and B. And let's look for the reals. So let's go ahead and look at solve that. Let's solve that value numerically. Solve it. And we can see some kind of nasty values here. But we have got our values.